Good evening, students. Let us continue the previous lecture of division. So now we have having understood the process, right? So in the previous example, what we did: 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, divided by, right? So 1, 0, 0, 0, 1. So what is the here it is fixed as 10 bits, right? So it is fixed as 5 bits. Also the quotient, this is the inputs, right? Inputs to the algorithm. So quotient is also fixed as 5 bits, right? Also remainder is fixed as 5 bits, right? So in this case, right, you know that we got the quotient as, right, 1 1 0 1 0, remainder as 0 1 1 0, right? So the so this case we got a quotient within limited 5 bits, limited 5 bits. So why we got like this? For example, you take this example. For example, let me show this. So this is what, right? Let me use the online calculator for explaining this. So this is what we did. So 0 1 1 0. Okay. So if we do this, so what we got? We got 0 1 1 0 1. So this is 1 1 0 1 0. That's what, right? 1 1 0 1 0, and remainder as 6 0 1 1 0. This is what we got. So this is within the 5 bits. For example, if I do this division, if I do this same division with this numbers, instead of 0 1 1 0, for example, let me take 1 1 1 1 0 0 0 0 0 0 divided by 1 0 0 1. So in this case, let us see what is the quotient and what is the remainder. Okay. So if you observe here, I am using calculator, right? If you give it as 1 here and calculate, you can observe here, right? So you get a quotient as 1 1 1 0 0 0. So what you got quotient as? Okay. If you ignore that 0, you got 1 1 1 0 0 0. Similarly, remainder you got as 1 0 0, right? So in this case, what you are getting? You are getting quotient as how many bits? 6 bits, right? Okay, remainder is within the limit. This is 4 bits. This is okay within the limit of 5 bits. But quotient, can you store 6 bits of quotient? If you get a 6-bit quotient, can you store? No, right? We are giving the fixed hardware for storing the quotient as 5 bits. But if you get a 6-bit result, this bit is missing, right? In the result, I can only accommodate 1 1 0 0 0. So this condition is called division overflow. This condition is called division overflow. How to detect this division overflow, right? This condition is called division overflow. It's a kind of an error or exception. Okay, why it is exception? Since we have a quotient of limited 5 bits, if we get a 6-bit quotient, right, that we cannot store in the 5-bit quotient, so that is considered as a division overflow, right? How to detect this overflow in an, like, it's a kind of exception handling in case of software. How to do that? So let me tell very quickly how to do that. For example, take this example. So 0 1 1 1 0 0 0 0 0 0 divided by 1 0 0 1. This is the first example we have taken. In the second example, 1 1 1 0 0 0 0 0 0 divided by 1 0 0 1. This is the second example we have taken. In the first example, the case is 0. So what we need to do is, for identifying the overflow, we need to compare the, so total 10 bits. Out of this 10 bits, we need to consider the first MSB 5 bits. So this we need to compare with this, right? So this 5 bits we need to compare with this bits, right? So in this case, what we got? We got 1 1 1 0 is less than 1 0 0 1. So since it is less than this, there is no overflow. That is how we need to do. So here 1 1 1 1 0, since it is greater than, right, the 1 0 0 1, there is an overflow. overflow. But in a reality, how to do in the hardware this comparison? You know the better way to do comparison is by 2's complement, right? 2's complement addition, right? So I need to subtract this by this, right? To subtract this by this, I need to take 2's complement of this and add. What is 2's complement of this number? 1, 1, 1, 1, 0. So do this 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, right? You do the addition. So 1, 0, 1, 1, 1, 1, 1, 1, 0. So the end carry is 0. Since the end carry, or in this case end carry is represented by a bit, since E is equals to 0, the end carry is 0, I can tell that 0, 1, 1, 1, 0 is less than 1, 0, 0, 1. So there is no overflow. If there is no end carry, there is no overflow. But in this case, what will get? You try this 1, 1, 1, 0, 0, 1, 1, 1, 0. Sorry, 0, 1, 1, 1, 1. So what we got? 1, 0, 1, 1, 1, 1, 1, 0, 1. We got a end carry as 1. So end carry as 1 means what is the meaning? 0, 1, 1, 1, 1, 0. Numerator is greater than the denominator. So in this case, there is a overflow. So first, before proceeding to the algorithm, we need to detect the overflow, right? How to detect the overflow? We need to consider the numerator of 5 bits, higher 5 bits, and subtract with the denominator 5 bits, right, with the 2's complement. So method. So after doing that subtraction, if we get a, with the addition, 2's complement addition, we get a end carry, means there is a overflow, right? So this we need to incorporate in the algorithm. This is a kind of exception handling. Okay. Now let us proceed with the algorithm. So this is the algorithm, right? Now see here. So the input is there in the A. Okay. So the input is there in the AQ. Numerator dividend is there in the AQ. The denominator is there in the B. Given this input, what we do first? So first we, of course, we can. This is nothing but the estimating the sign of the result. Okay, this is nothing but estimating the sign of the result. So how to tell the sign of the result? Based on the numerator and denominator signs, right? If both are equal, sign is positive. If both are not equal, the sign is negative. So accordingly, we can proceed the XOR operation and identify the sign of the quotient, right? So this is determining the sign of the quotient and the number of bits. How many bits I need to repeat these iterations that I initialize with the sequence counter. This is the sequence counter. I need to initialize with how many times I need to repeat this process. Okay. So first the process is detecting the overflow. How to detect the overflow? In this AQ by B we are doing. So this 5 bits I need to compare first. For that what I need to do for comparing, what I told, I need to do A minus B. So instead of A minus B, I can do A plus B bar plus 1 and I store the result in A. The carry will be there in the E, right? Just now I told, if the E equal to 0, what is the meaning? A is less than B. In this case, no overflow. We can proceed with the algorithm. But if E equal to 1, what is the meaning? A greater than B. Means there is a overflow. If there is a overflow, you just stop the algorithm. So same thing we'll do here, right? The same thing we're doing in the algorithm first. This is a kind of exception handling we are incorporating to our algorithm for safety, not for programmer safety, right? So without getting an erroneous error, we can incorporate such errors, error detection mechanism. So what if we get a end carry as 0, A less than B, right? So we can proceed with the algorithm, right? So here I have a provision to indicate a overflow, right? So generally what is the thing? We have this overflow. For indicating a overflow, I can have one bit called OVF, right? So I can set this bit. If there is a overflow, I can set this bit, right? By looking, if this OVF1, programmer understand that there is a overflow and he can stop the program. It's like that, right? So hardware just will set this bit indicating to the programmer that there is a overflow. If there is no overflow, OVF will be made by 0 and it will proceed with the algorithm. So same thing here. So first we start with the algorithm, check for the overflow, right? So I told the procedure, right? If there is a overflow, means E equal to 1, there is a overflow. If there is a overflow, okay, so just restore back the original value, right? So I did A minus B, A plus B bar plus 1, right? So just what I am doing here, I did A minus B and I put the value to A. Now I whatever the a value, original value I need to keep. For that what I do a minus b plus b and keep in a, so that the a value remains as it is, input remains as it is in a, that is the meaning here. I need to restoring the input back and make this OVF as 1, indicating there is error, and end the algorithm, so that programmer will display the message divide overflow, that is it. Okay. Now if there is no overflow, right, we need to we can proceed with the algorithm, right. If there is no overflow, we can proceed. So before proceeding with the algorithm, I need to again get back. So here I did a minus b, right, here I did a minus b. So to get back my original a, I need to again do a plus b, right. So to get back my original a, so that the input will be intact in AQ to proceed with the division, right. So I do a plus b to get back my original a and OVF 0, so get back the algorithm. So what is the algorithm? I divide, I first perform the left shift. So this I showed in the number of time iterations, right. First I perform left shift, right. After performing the left shift directly, right, if I do the left shift directly and e equal to 1, for example. So in the algorithm what I showed, I perform left shift. After performing the left shift, I do this 2's complement subtraction, right. Then I decide. So here there is a special case, like for example, if I do left shift, and e equal to 1 directly, I can tell that the numerator is greater than the denominator, right. I can directly decide, right. So numerator is greater than the denominator. So I decide here that numerator dividend is greater than the divisor. So I need to perform a minus b. I did that a minus b. Then I decided quotient is 1, right. This is a kind of same algorithm he is representing in a different way. He's taken some special case, like once I do left shift, if e equal to 1 directly, I can tell that e equal to 1 directly, I can tell that a numerator is greater than the denominator without even performing the subtraction. I can tell that. So so a minus b, after perform a equal to 1 directly, he did a. So without any ND carry, he came to the conclusion that, right, a is greater than b. So he did the subtraction. Anyway, we need to do subtraction, right, if quotient is 1. So did the subtraction and take the decision as qn equal to 1. This is fine. Now if e equal to 0, okay, then the common procedure what I told. So if e equal to 0, then we need to do the a minus b first, right, a minus b, and decide which is greater, a is greater than b or a is less than b. For that I am taking this decision. So if e equal to 1, a is greater than b. So if a is greater than b, what is the meaning? Yeah, quotient is 1, quotient bit is 1. I need to do a minus b. I already did a minus b, right. So I make decision quotient as 1, right. So but if a quotient, this ND carry is 0, if e equal to 0, what is the meaning? A is less than b. So in this case I should not do a minus b, right, but I did a minus b to get back my original a. To get back my original partial product, I need to do a plus b. This is called restoration, right. This step is called whatever I told, restoration, right, restoration step. So in this case qn will be 0. So qn will be, by default it will be 0, right. If it is, we need to make 1, we need to make 1, but in this case qn is 0, so by default it will be 0. So that is why we are not representing specially this qn equal to 0, that is it, right. Then we decrement the count and we proceed with the algorithm, right. So this is for the division algorithm. Finally after iterations, we get the quotient in q1, remainder in a, okay. The same algorithm, this extra step, extra thing he has provided, right. So now you can follow my step, right. Instead of this, you can do this directly. So you can do this directly, right, what I told and what he is telling. So what I told that shift left EAQ, this I told. So then you perform this a plus b bar plus 1, you do this first. I told like this, you do this, then based on the E, right, you take the decision. What decision I told? If E equal to 0, right, if E equal to first, okay, if E equal to 1, what is the meaning? A greater than B, okay. If A is greater than or equal to B, you need to make qn equal to 1, this is one thing, right. If E equal to 0 means A less than B, if A less than B, you need to restore back, what you need to restore back? A plus B, and store in EA and make Qn as 0, Qn as 0, right. Then you proceed with this sequence. This is what we implemented, the same thing here, same thing, the essence is same, but is a one special case is taking, right. First, after performing left shift, if E is 1, directly is ensuring that numerator is greater than denominator, right, and whatever the procedure you need to do is doing that procedure, that is it. Procedure is what? Subtraction, make quotient as 1, or if E equal to 0, we do not know whether numerator is. So, for that to come to know that, first we perform subtraction and we will come to know that subtraction using 2's complement addition, then we come to know whether A is less than B or A is greater than B. If E equal to 1, A is greater than or equal to B, in this case then quotient 1 and repeat this process. If less than 0, first you restore back the partial remainder, then decrement the counter and repeat. So, this process is repeated until the sequence counter becomes 0. Once the sequence counter becomes 0, the remainder quotient is in A, remainder is in A, quotient is in Q and remainder is in A. So, this is what. Now, so this overflow, I told whatever the overflow. So, this is one of the problem in the fixed point division. So, this overflow problem can be avoided in floating point. I will tell how we avoid the, in a floating point, how to avoid, we can avoid the overflow. That is advantage of floating point, one of the advantage of floating point division, right. In floating point division we can avoid the overflow. I will let you know how to avoid this overflow in case of floating. In case of fixed point we cannot avoid this, right. Thank you.